Sup nerds. Today I want to talk about Euler's method. Now this is a technique used to numerically solve differential equations that maybe we can't solve using some of the tools that we have. So first let's talk about the underlying idea of Euler's method, which is pretty intuitive in an everyday setting, but might seem a little technical in terms of equations. So we have y of t sub n plus 1 equals y of t n plus some h times the derivative y at t of n. So I like to interpret this as y of t sub n plus 1 is where you're going. That's the next step within your solution. And then y of tn is where you are. And h is your step size. And y prime of t sub n is the direction that you're stepping. So it's pretty intuitive that where you're going is equal to where you are plus the step size that you're taking times the direction you're stepping in. So you could probably visualize this just by standing up and taking steps and twisting around and taking another step. So that's the basis to Euler's method. Now if we want to draw this on the graph, the red dot would symbolize where you are, and then we could draw a slope given by the differential equation, and then we would take a certain step size h in the blue, and then the next point would just be we would continue the slope until we're at the end of our step size, and then we would draw the point there. And then we could continue this over and over, taking step sizes h. Now h is a parameter, h will vary. We could take steps of smaller size, which would give us more precise results, or we could take larger steps, which would be easier computationally. So let's take a look at an easy example where we have y prime equals t minus y plus 1, and the initial conditions y of 0 equals 5. And say we want to estimate y of 1. So the most basic version of Euler's method would be to do this all in one step. Now this isn't usually how it's done in applications, but let's just do it in one step so that we get a good feel for the method. So Euler's method would say that y of 1, which is where we're going, is equal to y of 0, our starting point, plus our step size. Now our whole step is a length of 1 times y prime of 0. And so we could easily compute y prime of 0 by looking at our differential equation. So y prime of 0 is just going to be 0 minus y of 0 plus 1. And so we just plug in the values, y of 0 equals 5, and we get that y prime of 0 is negative 4. And now we could return by taking this negative 4 and plugging it back in for our Euler's method equation and get that our estimate of y of 1 is 1. And we could draw this pictorially, just having our starting point at y of 0 equals 5, a slope of negative 4, and then continuing that little slope dash all the way down to the t value equal to 1, and giving that y of 1 is approximately 1. Now this isn't a very accurate estimate because we only used one step. We went all the way from t equals 0 to t equals 1 in one giant step. The way Euler's method is used in more applications is you use more steps. So let's take a look at how it works if we did it in 2 steps. So since we're going from 0 to 1 in 2 steps, each of the steps has size 1/2. And so our first step will take us from t equals 0 to t equals 1/2. And the equation says that y of 1/2 equals y of 0 plus our step size is now 1/2 times y prime of 0. And we already computed y prime of 0, and so we just plug everything in and we get that y of 1/2 is approximately 3. And now for our second step, we use this approximation for y of 1/2 in our approximation for y of 1. So y of 1 is going to be equal to y of 1/2 plus our step size 1/2 times y prime of 1/2. That's just the regular Euler's equation. And now we need to solve for y prime of 1/2, and to do that we use the differential equation and our value of y of 1/2. So going back to our differential equation, we plug in t equals 1/2 and y of 1/2 is equal to 3 to compute y prime of 1/2. And then once we have that, we have all of our pieces and we plug it into the Euler's equation and get y of 1 is equal to just 9/4. Now if we go back to the graph and this time look at what happens in 2 steps in purple. First, we're going from 0 to 1/2, and then we're adjusting our slope based off of the differential equation, and then we're getting a new slope and using Euler's method again to approximate y of 1. So we get y of 1 equals 9/4 this time, which is different from our first estimation, where we had y of 1 equals 1. Sometimes it's useful to organize all of the steps and data in one big table. So the first 2 columns of the table are really easy. It's just which step we're taking and the t value of the step. So we can fill those in pretty easily based off of how many steps we want to take. And then we want to compute what y of our t value is, what y prime of our t value is, and then what our next step is based off of Euler's method. So we'll go through this table and compute all of its values. So for the first row, we're looking at the 0th step where we start at t equals 0, and then we know what the y value is based off the initial conditions, and then we could compute the derivative based off the differential equation, and then we compute the next value, y of 1/2, which is 3. Then we take this value y of 1/2 equals 3 and plug it into the next column and use that to compute the derivative at 1/2. So we use our differential equation to get the derivative at 1/2, which is -3/2, and then plug in these 2 values into Euler's method to get our estimate for y of 1 and get 9/4. So for the last row, we don't have to fill out the last few values because we're just computing y of the last value. So we get y of 1. We don't really need to compute the derivative at the final point or use Euler's method at that final point. Now let's take a look at, say we're going to use 3 steps to estimate y of 1. So this time our step size is going to be 1/3 since we're going from 0 to 1 in 3 steps. So that'll require steps of 1/3. And let's use the table to organize all of the values. So here we have all the columns of the table. And the first row is usually really easy to fill out. It's just going to be our initial condition. So y of 0 equals 5. And then our derivative, we already computed, it's going to be -4. And now we're taking a step of size 1/3 with a slope of -4. So we're subtracting 4/3 from 5. And so y of 1/3 is approximately 11/3. And then we use this 11/3 to compute the value at the next point. So we find the derivative at 1/3 using 11/3 as our value of y. And then once we have our derivative, which is going to be -7/3, we use that in our Euler's method to find y of 2/3. So y of 2/3, after plugging in our values for y of 1/3, we end up getting 26/9. And now there's just one more step. We have y of 2/3 is 26/9. So we find the derivative at 2/3, and we get that the derivative is -11/9. Then we plug this derivative and our value for 2/3 into Euler's method, and we get that y of 1 is approximately 67/27. And you could compute what 67/27 is. Maybe plug that into a calculator. You get that that's around 2.48. So just to compare to 3 different steps, when we did it with 3 steps, we got 2.48 for our estimate. When we did it in 2 steps, we got 9/4, which is 2.25. And when we did it in 1 step, we got 1. The nice thing about this differential equation is we could actually solve it. Since it's a first order linear differential equation, we just rearrange it, use our integrating factor, multiply by e to the t, and integrate. We end up with a solution with y of t equals t plus 5e to the -t. And so when we plug in 1, we get y of 1 is equal to 1 plus 5 over e. So 1 plus 5 over e is about 2.839 ... And if we're comparing this to the 1 or 2 or 3 steps method, we see that the 3 steps is the most accurate. And this is going to be the case in general. The more steps you take, the more adjusting of the derivative you're making, and so the more accurate your answer is going to be. But on the flip side, it's computationally much more difficult to take more steps. So there's this trade-off between precision and computational difficulty involved with Euler's method. You see this trade-off immediately if you increase the number of steps. So if we do 4 steps, you immediately see that computationally it becomes much harder. I mean, you could still do it with pen and paper, and you get approximately 2.62 for y of 1, but the computations get messier, and we're getting a more accurate answer. So it suggests that it's really good to use this method using a computer program, which can compute it much faster than one can by hand. As always, I suggest that you work these examples out on your own and double check that you're getting the right answers. So make sure to go back at your own speed, and if you want, rewind and go over some of the concepts if need be. Last example I want to show y'all is an example that we don't know how to solve yet. So if y prime equals y squared plus t, and say we have initial conditions of y of 1 equals negative 1, and say we want to estimate what y of 2 is, then we can't use the actual solution the way we did in the last example. So you're really forced to use Euler's method in certain cases like this. So if we do it in 2 steps, then we could easily compute what y of 2 is. So this goes to show that Euler's method has plenty of applications in the real world, where you might be faced with certain differential equations whose solutions aren't nice and easy to compute. That's it for today. If you enjoyed the video, make sure to smash that like button and subscribe. If you have any questions or comments, drop them below, and till next time.